Well, good afternoon, everyone. Thanks for coming. We're broadcasting today from York University. I'm Kevin McGregor. I'll be your host for today. So it's my great pleasure to introduce today's speaker for the County Areas seminar series, Dr. Emily Hector from North Carolina State University. Emily is an assistant professor of statistics at North Carolina State University. She obtained her PhD in biostatistics from the University of Michigan in 2020, after which she joined NCSU. Her research interests are in distributed estimation and inference with applications in data integration and providing. Her recent work has developed methodology for the analysis of neuroimaging and wearable device data. She currently serves as an associate editor for reproducibility with the Journal of the American Statistical Association. She's originally from Ottawa and obtained her undergraduate degree from the University.
Thanks very much for the lovely introduction, and thanks so much for having me. It's a real pleasure to come back to Canada and have this opportunity to tell you a little bit about what I've been up to lately. So I think in this format, if you have any clarifying questions online as well as in person, feel free to raise your hand or you can just put them in the chat box. I'll try to keep an eye on that. If you have any more substantive questions, we'll keep those for the end. Okay, so clarifying questions during and then bigger questions for the end. So today, I'm going to present some joint work with two of my colleagues. So Brian is a colleague at NC State with me, and then Annie Aloyan, she's a professor at Brown University in biostatistics. And this work was generously supported by the National Science Foundation in the United States. So this is the award number. We always acknowledge our funders because we're very grateful for them. So a lot of my research, as was mentioned in my introduction, centers around distributed estimation, distributed computing. And so what I'm going to present today is really in this vein. I'm going to talk about how we can do distributed model building and then some integration, and the recursive piece will come in about halfway throughout the talk. And the goal here is really going to be to analyze very high dimensional spatial data. So if you are not familiar with spatial data, a couple examples. So one current example that's particularly relevant right now are climate data. So you can think here of some weather patterns or some temperatures or air pollution that is measured at a very high dimensional number of spatial locations, either across North America or potentially across the entire world. And so what we have is a very high dimensional data set where we have what are called spatial correlations or spatial dependencies. This is from the fact that locations that are close to each other are naturally going to be highly correlated, for example, in terms of temperature or in terms of air pollution. Another example here are ecological data. Here we might look at forest surfaces or migration patterns of specific animals. And so again, here what we're often measuring are observations at specific locations. And we have many locations. And so we have a very high dimensional spatial problem, where the dependence is really related to distances between locations. The particular example or analysis that I'm going to consider today is really kind of a little bit of a minor departure from these types of data. I'm going to be looking at neuroimaging data. The data in particular, they come from the ABIDE study, that stands for the Autism Brain Imaging Data Exchange. So this is a consortium of 16 sites across the US and Europe that aggregated, pre-processed, and then openly shared neuroimaging data on people who have autism spectrum disorder, or ASD, as well as what we call neurotypical controls, people who don't have autism. And so autism is a disorder that has really increased in diagnostic prevalence over the past couple of decades. And while there has been an increase in the diagnostic criteria, kind of a broadening of the diagnostic criteria, the increase in prevalence cannot be solely attributed to the broadening of those criteria. So in other words, autism is becoming more common, and so we need to be able to understand kind of what the etiology of the disorder is, be able to diagnose it as early as possible so that we can provide kind of some strategies to be able to live a long, happy, healthy life. So these neuroimaging data are what we call resting state functional magnetic resonance imaging, or RFMRI. So the R stands for resting and fMRI stands for functional magnetic resonance imaging. So these participants, they go to a hospital typically, and then they go and they lie in an MRI machine, and they go through a scan in this MRI machine. So again, this data set has data on many participants across the US and Europe who've undergone this MRI scan, both people with and without autism. And so what I'm going to talk about here are neuroimaging data. So I'm going to specifically consider locations in the brain in parallel to the climate data where we have locations where we might be measuring air pollution, for example. So a little bit more about the data type. This is really important to understand the biological or scientific question that I'm going to ask. And this is going to lead into the methods development as I move throughout the talk. So I have on the upper left-hand side here in panel A, different slices of the brain. So as somebody is kind of going through this machine, they're asked to basically just relax and rest. This is what we mean by resting states. They're not asked to think about any specific task. So this is really in contrast to what is called task-based fMRI. And so because they're just kind of lying there and they're relaxing, the RfMRI here measures blood oxygenation. Because it's resting, we call this the absence of a stimulus or task. And again, because it's resting, they're not asked to think about anything in particular. We think of this as really trying to capture the intrinsic brain activity. So how does your brain act when you're not doing anything in particular? All right, so this is kind of looking at this blood oxygenation level over a period of time as somebody is sitting in the machine. And this measurement is observed at different locations in the brain, which I'm going to call voxels. These are essentially three-dimensional pixels. Okay? And so what I have again in panel A are just kind of slices of the brain. We have many different locations. At each location, I observe a time series. That's my panel B. And what I'm ultimately going to be interested in is how different regions of the brain or different voxels are connected with each. All right, so this is that spatial piece. What is the correlation between different locations in the brain? Okay. So the reason why, so here what I've plotted in panel C is what we call a functional connectivity matrix. It's a sample covariance. That's all it is, okay? So it's a sample covariance where what I've done is I've taken, at each time point, I've averaged the signal at all the voxels in a particular region of the brain. These are the colors in panel A. I have several time series, and then I treat these time points as independent, and I take a sample covariance, and that's what I end up with in panels. And so the relationship between activated regions of the brain is essentially being captured here or characterized by this functional connectivity matrix. Okay, so again, this is just like a covariance between parts of the brain. Okay. So why am I interested in a covariance, right? Why is this the thing that ultimately I'm going to try to understand? So there's some evidence, and a lot of evidence actually, that has emerged from this ABIDE data set in particular that has shown that autism is what we call a brain disconnection syndrome. I want to point out here that this is disconnection with a Y, not an I. So what that means is that people who have autism have brain regions that are either hyper or hypo-connected, either over-connected or under-connected, right? In other words, they exhibit different connection patterns than people who don't have autism. Now, what I've plotted here is an example where I'm just looking at two regions of the brain. These are the left and the right precentral gyri. I've averaged at each time point, I've averaged the time point over all of the voxels. I have two time series. And so a very kind of simple, perhaps a bit naive approach would be to simply take the sample correlation between those two time series for each person, treating those time points as independent. And then I would have a univariate, a scalar sample correlation for each person. And then I might regress that on some covariates. So for example, autism status. And that is going to allow me to understand how autism influences the correlation between these two particular regions. Okay. So why am I developing a method here where there's already kind of a nice little approach that works? So while we basically have gotten the sense that autism is a brain disconnection syndrome, the evidence has actually varied substantially across different studies. What that means is that different studies tend to find very different results, and there's a lack of consensus and a lack of reproducibility of the results across multiple studies. So in other words, while we have a very vague picture, we don't have a very clear picture. We don't know which particular regions of the brain are hyper or hypo-connected. And one reason is that this approach right here, by averaging over all of the voxels in each of these two regions, is actually obscuring a lot of the variation in those regions, right? In other words, I've performed a huge dimension reduction here with this average, and I have probably averaged out a lot of the interesting and important signal that's occurring in each of these regions. So what we would like to do is to come up with a method that doesn't do an approach like this, that doesn't average, and that actually uses all of the data, all of the different pixels, all of the voxels, to try to obtain something which uses all of the data and is therefore more statistically efficient, more powerful, and hopefully we can come up with some results that actually do replicate across studies. Okay? So this is really the main motivation, trying to understand connections between brain regions where I don't want to do an averaging. I want to use all of the data that I have at my disposal to be able to answer this question. Okay? How does that correlation change with autism status and other covariates like age and sex, things like that? Okay, so that's the main motivation. Yes. Yeah.
That expectation of RI, is that an expectation over all the possible correlations we have each pair, or is it over, what's that over?
The expectation here is kind of over the distribution of the outcomes here, where the outcomes are those fMRI time series, and we're treating those time points as independent.
Okay, but have an expectation at each voxel, or?
This is averaged over the voxels, so it's an expectation for each person.
Okay.
Yes, yeah, at, where I'm looking at, the correlation between just kind of two measurements.
Okay.
Yeah, good question. Anyone else? Online? Okay. So I'm going to try to formalize this problem. I'm going to introduce a little bit more mathematical notation, and hopefully that will also help clarify some of these questions. So I have some independent replications. I'm going to call these, I'm going to index these by I. I'm going to say that I goes from 1 all the way to capital N, and capital N here is going to be my sample size, the number of independent replicates that I have. I'm going to ask you for the time being to ignore the time component and to just think about the spatial dependence, okay? Meaning that dependence between the voxels, between the locations in the brain. So I'm going to call YIS here, the time series at voxel S, right? So S here is the location in the brain, and I'm going to focus my analysis on just the left and the right precentral gyri. I'm doing this really mainly for illustration purposes. The method is already complicated enough as it is, but this does generalize. If I wanted to look at the entire brain, I definitely could. So all I'm going to do is I'm going to focus on voxels that are either in either of these two regions, the left and the right. And remember, I'm interested in looking at connections within those regions and between those regions. So I'm going to call the script D here the set of all these voxel locations. Okay? Now these connections, there's a lot of that, right? I'm looking at any connection between any two voxels in these two regions. So just for illustration purposes here, I tried to plot them. And you can hopefully see, just by the virtue of the plot here, how many connections there are. There's a lot, okay? So I'm going to talk in more detail exactly about how many connections there are and why this is a particular problem. So I'm going to introduce some model for my time series, my RFMRI time series at a particular location, and I'm going to assume that these are Gaussian, and I'm interested in looking at the spatial connections. Okay, so what I've plotted here, what I've written down here is the Gaussian likelihood. Sorry, just the Gaussian likelihood, where theta is some parameter that's related to the mean of the RFMRI and the covariance of the RFMRI. Not particularly important now. Theta is just some parameter. So you're familiar with this Gaussian likelihood, I hope. And so what I have here is my RFMRI outcome for person I over all of my voxels. That's my script D minus its mean. And then in the middle here is this covariance, this sigma. So this covariance describes the connections between all of the voxels. Okay? So the more voxels I have, the larger the sigma is going to be. If I have 3,000 voxels, for example, to store my sigma, I need 3,000 squared, approximately, big O, 3,000 squared memory, right? And here I have an inverse. So I need to be able to invert sigma, and that's going to take 3,000 cubed operations. So the more voxels I have, the harder it is to be able to compute this. I can't store sigma, and I can't invert sigma. And so actually computing a Gaussian likelihood for a very high dimensional number of voxels is going to become computationally intractable. Okay? How computationally intractable? That's the question, right? Can I still do it? So my data set here is 11 gigabytes, and I have my dimension of sigma here. I have on the order of 3,700 voxels that I'm looking at, and so my sigma has on the order of $13.5 million on the order. So very high dimensional, right? I can't store it, I can't invert it, and I especially cannot do this iteratively over any optimization algorithm that's going to be searching for some kind of solution, right? So I'm going to tell you a little bit more about the sample size in a minute, but my capital N here, if I multiply it by S, I have on the order of 278 million data points, right? So if I try to load this into R, I can't. If I try to do any kind of computation with this, it's just completely infeasible. So I need to come up with a technique that can actually handle the dimensionality of the data set, and the dimensionality here is large because of the number of voxels, right? Keep in mind the difficulty here is due to the dimension of sigma, which cannot be stored and cannot be inverted. So this is actually not a new problem. This problem has been around for a long time. I'm not saying anything particularly new or interesting here. There's a lot of techniques that have been proposed to address this problem. High-dimensional Gaussian likelihoods has been around a while. So I'm kind of just listing a whole bunch here. I'm not going to go through every single one of them. The two that I want to highlight are the first two. So composite likelihood, you have an expert in the department here on composite likelihood. So composite likelihood is essentially a low-dimensional approximation to that high-dimensional likelihood. It looks at, for example, pairs of outcomes, models their correlation, and then doesn't bother with higher order moments. Now you can imagine that if I have 3,000 outcomes, I need to look at every pair of those 3,000 outcomes. That's actually a lot of pairs. So the computation burden is actually still going to remain quite high. The next approach here that I'm going to highlight is called the nearest neighborhood Gaussian process. This essentially takes that sigma inverse and it assumes that there are a lot of zeros in it. It is kind of a sparsity assumption on that sigma inverse. And that means that it's a lot lower cost to store it, and you actually don't need to really invert it at all. Okay? So I'm going to compare some of my methods to this method, which is why I'm highlighting it here, the nearest neighbor Gaussian process. Now, a lot of these methods don't get over the burden of actually loading in your data, right? They assume that you can still load your data and that it's just computationally intensive to compute with your data. And then you can use some of these methods, right? So that's kind of the first limitation there. And then the second limitation is that most of these methods assume that kind of sparsity in that precision matrix. And what that means is that you are essentially assuming independence or maybe conditional independence where it's an approximation. And so there's a loss of efficiency that happens there. And so kind of that approximation can actually result in something which is perhaps not quite as statistically efficient in terms of minimizing those variances as an approach that actually does capture and model all of the dependent structures. Okay? Now, sometimes that's fine, but sometimes it isn't. Okay? So these are kind of the existing methods, and again, the two top ones are the ones I really want to highlight, but broadly speaking, these are not going to be as fully efficient as perhaps what I would like. And so what I'm actually going to propose today is how to estimate and do inference for mean and covariance parameters of this high-dimensional Gaussian likelihood, and I'm going to do this in a distributed framework. And my approach that I'm going to propose is going to be computationally really efficient, it's going to be really fast, and it's also going to be statistically efficient. That component is actually really important. It turns out that it's not that hard to do things that are computationally fast, but it's hard to do them in a way that actually captures all of that dependence and remains statistically efficient, right? The real challenge is being able to do both of these things together. So the key ingredients, and hopefully you'll remember other pieces of my talk, just in case you don't, these are the 3 things that I want you to remember after today. So I'm going to talk about a spatial partitioning approach. That's the distributed component. I'm going to kind of break up my data into small blocks. I'm going to talk about the generalized method of moments. That's going to come into how we combine at the integration step in a way that is statistically efficient. And then I'm going to talk about optimal estimating functions. That's going to come in much later in the talk. And that's going to be a technique that we use to actually maintain that statistical efficiency gain that we get from the generalized method. Okay. This is very high level, broadly speaking, this is our roadmap. Okay. So let's start to formalize our model, start to formalize kind of the assumptions that we're going to put on our data. So my RFMRI time series, my RFMRI outcome is going to be denoted by this yi at a voxel location x. I'm going to assume that it can be written as a sum of 2 terms. That first term alpha is going to characterize the spatial variations. It's going to capture how the RFMRI outcome looks like over space. And then I'm going to assume that that process is observed with noise. And that noise is going to be denoted by this epsilon I. These are IID normal with some mean 0 and some homoscedastic variance sigma squared here. It's assumed independent of alpha I. This is a very standard model in spatial outcomes. For each I, I'm going to assume that I also observe some explanatory variables, some covariates. I'm going to assume that there's Q of these, and I'm going to denote them by xi of s. So you can think here, for example, autism status, age, sex, and so on. You'll notice here that I'm allowing these to vary over space. That's also to allow these methods to work with, for example, climate data, where I might want these covariates to include longitude and latitude, for example. Okay? So the model is flexible enough to allow for these covariates to vary over space as well, meaning that at each location, the covariate might be different. Now, in my abide analysis, what that might look like, so I'm going to bring it back to my examples so we can think about this hopefully more concretely. My yi of s from I equals 1 all the way to n, this is going to be the thinned RFMRI time series at voxel x, and here I'm going to have 774 abide participants that have passed quality control. So what do I mean by thinning? What I mean is that I'm essentially going to remove every second time point in that time series, and then I'm going to treat those time points as independent. That thinning process, that dropping of every second time point, removes the autocorrelation that we see in that time series. One of the main reasons I can do this is because it's resting state. So because it's resting state data, they're not supposed to be thinking about anything in particular, so the autocorrelation is actually very, very weak in that time series. And so dropping those time points is going to make this independence assumption pretty valid. So what I end up with are actually yi of x here, where I is going to index not only the independent participants, but also these independent time points from this thinned time series. And so I'm going to have a sample size here, which is not 774, but actually on the order of about 76,000, because I'm looking at all of the independent time points for each individual, and I'm counting those as well. Okay, so now this yi of s is the outcome at a time point for one person at voxel s. Okay, and the I indexes both time points and people. And then finally, these covariates, these xi of s's in my abide data analysis, these don't vary over space, so I'm just going to call them xi. Here I'm going to include an intersect, my autism status, age, sex, and then the interaction between age and autism status. Okay. So these are the covariates I'm going to be interested in. So remember, my goal is to understand how these covariates influence the covariance of y, right? That's my ultimate goal, where that covariance is very high dimension. Okay, so moving on a little bit more then. So my alpha I, I'm going to assume that this is a Gaussian process. These RFMRI outcomes are typically mean zero centered and also scaled to have a variance of 1. And they actually do end up looking pretty Gaussian after those transformations. And so we'll assume that alpha I here is Gaussian. I'm going to denote its mean by this mu. It's allowed to depend on the covariates as well. And I'm going to assume that it's fully known up to some parameter of interest, which I'm going to call beta. So for example, mu could just be xi transpose beta, for example, right? It could be a very simple function of both my covariates and some parameter beta, for example. I'm going to assume that the covariance of my outcomes over space is described by this positive definite covariance function C alpha, which itself is known up to a vector of parameters of interest, gamma. And here it's really important, this covariance is allowed to depend on the covariance. Remember, right? I want to know how does autism influence the covariance. And that is going to be described by this gamma along with some other covariates potentially as well. Right? Now, this is pretty atypical actually for spatial models. Having covariance in the covariance is not common because it introduces all kinds of issues with positive definiteness. And so I'm going to introduce what this model looks like for my abide data. And I promise you now, it is positive. Okay. And so at the end of the day, what I'm interested in estimating and doing inference on are both of these two parameters, beta and gamma, as well as my error variance term, sigma squared. This is also called a nugget variance term. And so I'm just going to say that the dimension of this whole theta is p. And so I'm interested in, again, carrying out inference on the mean covariance as a function of this theta parameter. So far, pretty standard, I think. So what do these models look like specifically for abide? So for abide, my data are centered to have a mean 0. And so it's a fairly reasonable assumption that the mean is actually the same at all the locations for every person. And so I'm just going to parameterize it by a scalar beta. The scalar beta should be close to 0, right? Because these have been centered to have mean 0. Where the real interest lies is in the parameterization of this covariance. And so this model here is not my proposal. This is kind of a slight modification of some other people's proposals for how to incorporate covariance into the covariance. The key point here is that I have a spatial distance term, which tells me how far two voxels are from each other. That's this Sj prime minus Sj squared term right here. And then in the denominator, I have these rho ij's, rho ij primes, and they also show up in front. Those rho ij's are where I'm putting my covariates. So my covariates are influencing the correlation through these rho ij terms, these rho ij prime terms. And so what I'm really going to be interested in is actually estimating that rho parameter right there that tells me how my covariates, including autism, influence the correlation between different voxels in the brain. Okay? This is my model. This is going to be the covariance that I'm going to assume. And so my goal is to estimate rho. Now, this is actually quite difficult with spatial data because what happens is that now I don't have just one covariance matrix for all my people. I have a different covariance matrix for each person. So that inversion, which was on the order of s cubed, is now s cubed times n because I need to do it for everybody because everybody's allowed to have a different covariance. So this model actually makes the computational burden even larger, makes it explode. And this is really due to the fact that I have kind of this non-stationarity that's introduced here with this rho ij term down here. Okay? So this is what we want to do for abide, and unfortunately for us, it makes the whole problem even more computationally intractable than what it was before. So I've already told you, I've given out the first punchline away, right? I'm going to do a distributed approach. And so I've told you I'm going to use what's called spatial partitioning. What that means, I'm going to illustrate this on a two-dimensional domain because it's kind of hard to show on the brain. But if I had a two-dimensional spatial domain, so these are 160 squared locations, and these are the outcomes at all of these locations that are plotted in color. What I'm going to do is I'm going to take, so you can think of this as a map, right? It's a map of a very square country. And so what I'm going to do is I'm going to block these locations into very small groups of locations. So right now here, I have 25 locations in each of these very small blocks, okay? So I'm just going to throw out some lines that are going to partition my big domain into relatively small groups of spatial locations. And then I'm just going to consider one of those spatial blocks, one of these little blocks, so for example, the bottom right-hand side. Oh, sorry, one more step. So just to illustrate, right, I'm going to look at my full data set, I've partitioned it, and so I've partitioned it into all of my small blocks. And I'm just going to label them one all the way through K sub M. Okay, so I have K sub M blocks here. That's the number of blocks that I've divided into. Now, each of these is relatively small, as I was saying, and I've ahead of myself a little bit. So because it's small, that means that the likelihood in each block is actually really tractable, right? Now I'm trying to estimate these parameters based on a very small number of locations. So that covariance matrix inside that block is actually very low dimensional, which means that I can store it, I can invert it, and so on. The really nice part about this is that I actually don't need to load my whole data into my R section. I only need to load in that very small block. So for example, only a small number of voxels in the brain, I only load those into my R session, and then I'm going to treat them as if I had no other data. I'm going to estimate my parameter based only on this small number of spatial locations, because again, the likelihood is tractable. And so I can easily obtain my maximum likelihood estimator, and I'm going to call that maximum likelihood estimator theta hat K sub M. And it's an MLE, so it's the root of a score function. This is the Gaussian score function. I'm not going to write it down because you all know what it looks like. But the important thing here is going to be the notation. So theta hat here is the root of this score function, which I'm denoting by this capital psi. And it's an additive function over my independent observations here, I1 through M. Okay? So once I have my estimator, I might be interested in estimating its variance, for example. And so I'm going to be interested in things like the sensitivity matrix down here. This is the derivative of my score function. And then I'm also going to denote this psi hat here, this kernel estimating function. The kernel here means that it's evaluated on only one independent observation, but where I'm going to plug in my estimates. Okay. So this is the point that I'm at. I've analyze all of my data sets, and because I only need to load one into my R session at a time, I might even do this in parallel. So not only is the analysis of each data set really fast, but on top of that, I can do all of these simultaneously. And so the total runtime here is actually only constrained by the runtime of the slowest block, right? Which is why I've tried to make these more or less all the same size, because that way they take all about the same amount of time. And I'm going to return a couple things. I'm going to return my estimator, this sensitivity matrix, and then this kernel score function right down here. And so now the real question is, okay, I've obtained estimates across all these small blocks across my whole domain, and that's great, but I just want one estimate, right? So I need to find a way of basically combining these all together, right? And then I'll be done, and everything will be great. So in order to do that, what I'm going to propose is that we take these estimating functions and we stack them one on top of the other. Okay? So each of these is p-dimensional, put them one on top of the other, so the total result is p times km. And I can do the same thing for the kernel estimating function. And now what I'm going to try to do, and because this psi here now has p times km dimension, my parameter is over-identified. I have more estimating functions than I have dimensions on my parameter. So I can't just set this equal to 0 and solve, because I have too many equations, right? So what I'm going to do instead is take a quadratic form of this psi function, and I'm going to minimize that instead. This quadratic form, it's important to know that I'm going to use as a weight matrix this covariance matrix. This covariance here is estimating the covariance between the estimating functions. Right, I'm going to say that one more time. This v hat is estimating the covariance between the psi hats, or the psi's rather. And all it is it's a sample covariance. So it's non-parametric, it's relatively easy to compute. Okay. So this is just a sample covariance, and it's capturing the covariance between the estimating functions. And I'm going to argue that that means that it captures the covariance between the blocks, the spatial covariance. So why is that piece true? Well, it turns out that if you look at the form of this kernel score function, and you look at the covariance of this kernel score function over 2 blocks, and you just plug in what that kernel score function is, you actually get that this is a scaled form of covariance of the original outcomes. And so they're not the same, but they're capturing the same thing. Okay? So whether I'm using covariance of the y's, the covariance across the outcomes in different blocks, or whether I'm using the covariances of psi's, I'm actually describing the same thing. I'm describing the dependence between the outcomes in different blocks. Okay? And so this is really important because this is the key to capturing that dependence between those blocks so that I can maintain that really efficient estimation as I combine, right? And so that I can get valid inference. I can calculate the variance in my estimate. So hopefully I've convinced you that this V hat is capturing dependence between blocks. And so at the end of the day, what I'm going to do, this quadratic form here, I'm going to put in this V hat right here inside this weight matrix. This is a generalized method of moment estimator. This is really important work. This man won the Nobel Prize for, I'm sure, other things, but this work among others, right? So I can minimize this quadratic form and I get an estimator that is now combined over all of my data, and it incorporates dependence across all of those blocks of my data. So it's statistically also really efficient. Okay. Unfortunately, minimizing this means I have to re-access every single data block to evaluate my score function over at every candidate data. So this is not ideal. So in a sequence of papers, I and some collaborators showed that the minimizer of this estimating function is the same as this meta estimator. And there's no iterative minimization here. We take the estimator, we weight it by some function of its variance, and then we sum them all together. And then we have a scaling term in the front that makes sure that the estimator remains consistent. Okay. So this is actually not what I mostly want to talk to you about, but this is really important background to understand where I'm going. Okay. So this estimator here is computationally really fast because all I've done is I've analyzed small amounts of data in parallel, and then at the end, I don't do any optimization. I take a weighted average. Right? It's computationally really fast. It's also statistically efficient because I've used this V hat matrix. I've captured the dependence between the blocks, and that's allowed me to leverage and borrow that dependence to minimize the variance of my estimator down here. So it's statistically really efficient. Right? Those are my two goals: computational efficiency, statistical efficiency. Great. Okay. So this is where I'm at. I've taken all of my estimators and I've used these things to get this estimator down. Okay? Great. So what's the problem? Well, unfortunately, that's not the end of the story. So this is the estimator that I had on the previous slide. And I've kind of glossed over this V hat. I've glossed over its dimension. So its dimension is P times KM. So if I have 100,000 locations, and I want to divide those 100,000 locations into small blocks, let's say blocks of size 25, I need 4,000 blocks. So that means that Km is 4,000. And that means that P times Km is actually still kind of large. So what that means is that in really high dimensional problems, if at the end of the day I need a small block, I need a lot of blocks. And so if I stack this all together, the dimension actually remains really high. It's not as high as the original S-dimensional covariance matrix, but it's still high. And so this inversion here, it can be impossible if by accident this PKM gets bigger than N, and then I get something that's not full rank. But even if it's full rank, it can be computationally expensive, right? I'm inverting a very large matrix, and we really like to avoid that. So unfortunately, this is not the end of the story. I can't just stack all of these things together and actually invert this and then get an estimator at the end of the day because of this computation burden right here. So the challenge is that I have too many blocks. I'm trying to integrate across too many blocks. So I need to come up with something slightly different. One idea might be to only combine over some of the blocks, right? Then I would have a much smaller KM. So if we kind of take that idea and run with it a little bit, what I'm going to propose is a recursive partition. What that means is I'm not going to divide all at once into small blocks. I'm going to divide and then divide again and then divide again, and I'm going to keep going. So I'm going to call these resolutions. The notation here, unfortunately, gets a bit complicated. So I'm going to try to not talk about the notation too much. But if you are curious, this is the 0th resolution. This is the first resolution. This is the first split. And here I've split into k sub 1 blocks, right? I have 4 blocks. And then I'm going to take each block and I'm going to split it again into 4 blocks. And unfortunately, the color is not great here, but hopefully you can see that I've added more lines here. So each block is being further divided into 4 blocks. So my k sub 2 here is telling me how many blocks do I have inside of my first one, and that's 4. That's my second resolution. I'm going to go on. Third resolution, I'm again going to divide, and I'm just going to keep going until, at the end of the day, each small block is small enough that I'm happy with its dimension that I can easily analyze it. So this partition is actually the same as the one that I showed you earlier, except that now I'm thinking about it as kind of nested partitions, right? Nested groups. And so what I'm going to do is, again, this is identical, right? I have all of my blocks just like I had before. I'm going to analyze all of my blocks just like I did before, except that now instead of combining everything at once, I'm only going to combine, let's say, those that are in that nested resolution, right? In that nested partition. So now this is only 4. So this is 4 times p. This is very low dimensional. I'm going to use the same formula that I did earlier. Okay? So this is really easy, really fast. It's computationally efficient, statistically efficient, and so on. But the question is, so I still have a lot of estimators. So I need to keep going. I need to keep combining them over and over and over again. And this is that last key ingredient that I mentioned. If I keep doing this and I keep stacking over and over and over again, I actually end up with another high-dimensional problem. It's not ideal. If I keep stacking, at each step, I'm multiplying by another km. I'm multiplying by another number of blocks that I have. And so if I keep stacking, at the end, the dimension is going to be like this, p times k1 all the way to km. And so I've actually not reduced the problem. I've kept the problem growing at each combination step. And so the last ingredient, the last trick, is to not just keep stacking them, but instead, at each combination step, to project them into a lower dimensional space, in particular, a p-dimensional space. Okay? The way that I'm going to do this is using what's called an optimal projection that's going to minimize the variance of the estimator of that estimated function. These are the most technical details. I promise this is my most technical slide. So what I'm defining is I'm multiplying, remember that old friend, that sensitivity matrix, that old friend, that variance matrix. I'm pre-multiplying it, and now it's p-dimensional. It's no longer pkm. I've projected it into p-dimensional space. And again, this projection is optimal in the sense that it minimizes the variance. And now I can stack, right? So instead of stacking the original size, I'm stacking their projections. And now the dimension is going to stay small. And so I'm going to keep projecting at every step of this iteration. And at the end of the day, I'll get my combined estimate. And so at each step, I'm only inverting very small matrices. And I am only doing these kind of meta estimators, these one-step combinations. So I think this figure illustrates it best of all. So this is an example of recursive partition. These are all of the blocks that I have. So I might combine, for example, these 3 together. And I'm going to have to invert a 3 by p matrix. And I'll get this estimator right. And then I will combine these 2, and I'll have to invert a 2 by p matrix. So again, very low dimensional. And then at the end, I will combine these 2, and again, I will invert a 2 by p matrix. Okay. So at each step, I'm inverting a matrix, which is kr by p, where kr is the number of blocks that I'm combining. Very few, right? Because of this recursive partition framework. And so at each integrated step, I'm getting fewer and fewer estimators that I'm gradually kind of combining. So you can think of this as, I have my big domain and I'm combining things that are close to each other, and then I'm aggregating them, and I'm basically combining things that are closer and together. And at the end, I get this global estimator theta hat bar at the top here, which is combined over all of my domains. So it's computationally really fast because of these small inversions, these parallel computations on a small block. It's also statistically efficient because I've used the generalized method of moments and because I've used this optimal projection. Now, it's actually kind of hard, and I'm skipping over all of the theory. You can show that this estimator is consistent and it's asymptotically normal, and you can estimate its variance. The proof here is by induction, if you're curious. It's pretty technical, so I won't talk about it too much. So, but you can do, the point is that you can do inference. You can get an estimator, you can estimate its variance, and you can get a confidence interval and so on. And massive computational gains, but I put ... here. This point is hard to convey in talks. And that's going to show you how fast this is with simulation, right? This is really fast. So I'm going to consider just a very small example just to get us started. This is a small example that means that I can easily compare to other methods. So I have a 20 by 20 two-dimensional block. And so that means that I have 400 locations. I'm going to split them into 2, and then into 2 again, and then into 4. And I have 10,000 outcomes and a very simple covariance structure model and a mean model. Very briefly, these are asymptotic standard errors, empirical standard errors, and root mean squared errors. The leftmost point is the nearest neighbor Gaussian process that I told you about. And then all of these are different ways of combining, depending on how you split. The point here is that our estimator gets the same statistical performance as kind of this preferred technique that's currently used in literature. So statistically, it does as well as this approach that uses all of the data. And then this middle one down over here is another approach that doesn't do so well. Okay? So statistically, it's capturing all of that dependence. It's very statistically efficient. Computation times, again, small example. Okay, so our approach runs in about 0.8, 0.66 seconds. Okay, the nearest neighbor Gaussian process takes 280 seconds. So in this small example, we are 350 times faster than the competitive approach. I coded this myself using RCPP and sparse matrices for the nearest neighbor Gaussian process. This is my best attempt at making it competitive. Okay, and we're still just so much faster. And this is kind of inevitable, right? Because we're looking at small amounts of data, and then we're combining everything with no optimization procedure. So really, our computing burden is solely the slowest small block. And that's typically going to be really fast. Now, I have some more simulations here that are in the setup considered in the data analysis. I'm going to skip over these just for the sake of time so that we can get to that data analysis. Just to reassure you that it works in a simulation that looks like the real data, right? So here are coverages. The coverages look great. They're all about 95%, which is a nominal level. And so this gives us confidence that we can move forward with that really complicated covariance function that I was interested in using. Okay? So coming back to my, my data analysis, I'm looking at voxels, and again, the left and the right pretty central gyri. And so I have on the order of 3,700 voxels. If you remember, this is 13.5 million covariance variant values. My covariates here at the intersect, autism status, age, sex, and the age by autism interaction. So these, on the order of 3,700 voxels, I'm going to partition them into 2 and then 4 and then 4 blocks. Remember this recursive partition? First, I split them in half. Then each half gets split into 4. And then each of those small, again, gets split into 4. Okay? And then I perform this recursive integration that I've just described to you. So these are the estimates in my, my data set. And for comparison, I also did this on all of those time points that I threw out. Those time points that I threw out are not different in any way from the time points that I'm actually analyzing. Okay, so what I'm doing here is I'm evaluating the robustness of my method and my model across 2 data sets that should be identical in every way. Okay, so this is because robustness in neuroimaging studies is a really difficult problem in the sense that you can analyze very similar data sets using the same method and get very different results. So I'm trying to evaluate here whether the method is giving me the same result in data sets that should be the same. And for all intents and purposes, the estimates are the same. Statistical hypothesis tests actually tell us that they're different. And that's just because the method is so powerful that it can detect really tiny differences, right? So what we do is we calculate a data-dependent type 1 error rate. This is just the 5th percent quantile of the observed p-values. This is an idea really closely connected to knockoffs, essentially. So I'm basically just trying to modify my critical value for hypothesis testing so that I can accurately reflect what I think is a practical difference in effects in my study. And so what we show is that autism manifests as hyperconnectivity, meaning higher connectivity between and within regions of the left and precentral gyri. This actually concurs with some existing literature, and it also concurs with that traditional analysis that I mentioned all the way at the beginning, where we averaged over those voxels. Estimates are actually really similar, but that traditional analysis finds that autism is not significant. Whereas in our approach, because it's more efficient, we show statistical significance of the autism. So there's actually a real advantage to using all of these data that we have collected and not averaging, because we get something which has a narrower confidence interval, and so we can actually claim that the autism does significantly influence this connection between and within these brain regions. Okay, so with that, I will wrap up. So just a couple limitations that I didn't have time to dwell on. I get asked this question often when I talk about divide and conquer methods. Yes, these methods do depend on how you partitioned your data. Okay, so you can do different partitions and evaluate how much your results change depending on that partition. This is kind of like a sensitivity analysis. I have some other work with one of my students that's ongoing, where we look at whether we can kind of estimate a good dependence, a good partition, to try to remove the influence of that partition. But there's some kind of work in this space. Ideally, the results don't have, the estimator is still consistent, right? So it's still estimating the same thing, and so asymptotically, these differences should wash out. Our asymptotic here are in sample size, so you do need a large sample size to estimate that V-hat matrix. You need to be able to infer, okay? My implementation here doesn't allow my parameters to vary spatially, but that would be a fairly straightforward extension. And then I'm also interested in more flexible models of the between ROI correlations. Remember that C function I showed you? It's mainly for modeling within ROI correlations. The model between is a little bit more restrictive. And so we're interested in looking at extensions. So with that, our paper is available on arXiv. It's right at the top here if you're interested in reading about it. It just posted an updated version very recently. And then I would like to thank you again for the invitation and your attention. I'm happy to take some questions. And I'll keep an eye on the chat.
Thank you so much for an excellent talk, Anthony. So yeah, we're going to open up the floor to questions now. So I don't know if we have any questions in-house. If you want to ask a question over Zoom, feel free to use your microphone or just type into the chat. If you have any questions here. If not, then maybe I'll start by asking a question. So you have a very particular covariance structure. So what is the background and the motivation of that variance structure?
Yeah, that's a really good question. So just for the online audience, the question was, to talk a little bit more about this covariance structure that I have, or this covariance model, and basically what's the background. So the original proposal was, it's a really nice paper by Patrick and Shervish, where they propose a covariance model that looks a lot like ours. And the goal is to allow for the incorporation of covariance while maintaining that positive definiteness and still having that spatial component that decays. So it is very closely related to a kernel of a Gaussian or an exponential covariance function, but we have kind of these more complicated pieces in the front that allow us to keep. Let me see if I can put it up on the slide here. Okay, we have kind of these more complicated pieces in the front here that allow us to maintain that positive definiteness, right? So these pieces are actually like really important. And so this is, you can think of this as kind of an average of correlations of these kernels at kind of different locations. The locations J prime and J here in particular. And what I'm doing is I'm kind of averaging those two kernels down here. And this is why I say that the model is primarily intended for within correlation, right? Is that I'm looking at ideally small distances and how they change over an average of those correlations in two different dimensions. And so that non-stationarity piece really comes in here with these IJs and IJ primes. Where I'm allowing the direction of decay to be different depending on whether I'm looking at J or G. Yeah.
Is there like an easy interpretation of the effect of the covariance?
Yeah, is there an easy interpretation for the effect of the covariance? This is actually one of the places where we really struggled in the paper. So fortunately, we're dealing with a dichotomous covariance. And so what I've done, and I hesitated on putting this in the slide, maybe I should have, But what I did is I computed those covariances, whether you have autism or not. So because it's 0, 1, you can actually, compute those and you can look at those values and compare them, and you can kind of evaluate that if that's the effect size, essentially. For continuous covariance, the best I've been able to do is a plot. Yeah, because it is very nonlinear, right? And so it is difficult to interpret. So plotting, and then for dichotomous covariance, being able to just plug in those two values is how we've done it. Yeah.
Yeah, I did something very similar.
Yes. Yeah, exactly. Yeah.
There is one question.
Yes. Yeah. So somebody in the chat session asks, how do you choose the optimum resolution level to do a nested partition? This is a great question. So there is some literature in the spatial statistics on choosing partitions, and so there's some advice that exists out there. The advice that I would give is that you want locations that are close to each other so that you can capture close dependence, and then you want to make sure that you're going far enough out that you're capturing that decay, meaning that if all of your locations are really, really close, you're going to have a very narrow range over which to estimate these parameters down here, because you're not going to see enough decay to be able to estimate those parameters. So I'll repeat that one more time. You want locations that are close, and then you want to make sure that your box is large enough so that you can capture that decay, so that you can estimate these parameters consistently within each block. Now that's for the estimation. There's this double challenge where you want to make sure that that box is not too big, because otherwise you run into computational difficulties. And so there's a real trade-off here where making sure that you have enough locations in that small block to be able to estimate your parameter consistently, and not too many locations that it's computationally intractable. So in practice, in our simulations and actually in the data analysis, we found that kind of 25 to 100 locations was typically sufficient. But it does depend on the range of the spatial locations, right? It does depend on that distance. So I guess, if I was putting on my data analysis hat, I would probably look at a covariogram and look at kind of that range of that decay over different spatial lags and things like that. There's ways to kind of troubleshoot it, and then we kind of have these rules of thumb of about 25, 100 locations. Hope that answers your question, but feel free to tell me if not in the chat box.
Any other questions from the audience in person?
Picking up any other ways of partition, like if instead of divided to blocks, if we do clustering,
Yeah, this is a really good question. So the question for the online audience is, are there other ways of doing the partitioning, for example, clustering? Yes. This is actually one of the projects that my student is working on, where we do a clustering approach to try to learn which ones are actually dependent enough that it's worth putting them together to estimate that dependence kind of most efficiently. It's actually a really hard problem, and so because it's a clustering on covariances. So we have one paper on arXiv that uses a hierarchical heuristic process. The mixing was really challenging, so we came up with some techniques, and then my student's working on a next approach, which I think is more sophisticated, that uses kind of a block model for this covariance, and so you end up with clustering on your covariance that's a lot more flexible, essentially. So that's the long answer. The short answer is yes, you can do clustering, but it's hard. Yeah, and it kind of depends on what your downstream goal is, but if you want inference, it's even harder because you need to be able to estimate the variances. And so any kind of penalization approach, you lose the ability to do inference, in my opinion, at least. So Bayesian approaches work pretty well in this, but then the computation burden is really high. Yes. One more question in the chat. Oh, she just said thanks, that is clear.
Any other questions?
Any last minute questions?
One more. No one else, and maybe I'll just ask one more. So if I'm understanding correctly, you didn't have to make any sparsity assumption, right?
That's correct. We did not have to make any sparsity assumptions in the covariance. That's right. Yes.
So are you then restricted the number of boxes Sample size or anything like that, or?
So are we restricted in the number of voxels that we can include relative to the sample size? The only constraint is that the maximum number of blocks that I've ever integrated multiplied by p has to be relatively smaller than n.
Okay.
Yeah, so with a lot of voxels, that becomes more challenging, right? Hence the recursive approach. So that problem is actually really mitigated by the recursive integration approach. Yeah, so that's actually one of the main reasons that we did yeah. Does that make sense?
Yeah, absolutely. Okay, perfect. Well, please join me in thanking everyone for time.
Thanks very much, everyone in person and online.